Analyzing the evolution of environmental impacts due to fish farms expansion. A pilot study in the northern Nile Delta. Abstract: transforming the agricultural lands into fish farms leads to several negative environmental impacts. This research paper aims at analyzing the environmental impacts of the privately operated fish farms expansion in two study areas in the north of the Nile Delta of Egypt occurred during the period 2014 to 2018. The analysis considered fish farms' water requirements, consumption, effluent disposal, drainage rates, drainage water quality, groundwater heads and salinity, and socio-economic aspects. Multispectral Landsat-8 images was used to determine the change in fish farms area between 2014 and 2018. The principal component analysis, PCA, was conducted before classifying the images. The classified images combined with actual measurements and scientific analysis was used. This research focused on a pilot area about 637,755 feddans, acers, located in the northern parts of El-Gharbia Drain Catchment and the southern parts of Lake Burullus in Egypt. The overall increase in privately operated fish farms area was estimated at 7.42% in the study areas during the period 2014 to 2018, equivalent to 18,419 feddans. The estimated increase in water requirements for the fish farms was 17,803 m3/feddans/year, equivalent to 82.0 million m3/year in the study areas during 2014 to 2018. Ratio of water requirements, fish versus crops, in the study areas was almost double. The increase in disposed effluent from the privately operated fish farms, including high biological and nutrients loads to either nearby drains or lakes, was 5,756 m3/feddans/year, equivalent to about 26.5 million m3/year from the study areas during 2014 to 2018. Nevertheless, the resultant was a decrease in drainage rates in the study areas by more than 30%. That decrease could be attributed to the increasing unofficial reuse of drainage water for irrigating agricultural crops as well as the expanded fish farms activities in the study areas. Consequently, high water pollution concentrations were monitored in El-Gharbia Drain during the period 2014 to 2018. Some parameters exceeded the environmental law limits by several folds. The privately operated fish farms expansion in the study areas contributed to the deterioration of water quality of the final reaches of El-Gharbia Drain as a result of disposing fish farms' effluents. Consequently, the privately operated fish farms in the northern Nile Delta inherit various environmental impacts, thus should be strictly banned and/or controlled as one of the rigorous actions to alleviate water pollution in Egypt. Keywords: impacts of fish farms, aquaculture, drainage rates, agricultural drainage water quality, groundwater heads and salinity, economic and social impacts, El-Gharbia Drain, Northern Nile Delta of Egypt, PCA, change detection. Introduction. At a global glance, the main fish farms, aquaculture, producers in 2016 were China, 49.2 million tons, India, 5.7 million tons, Indonesia, 4.9 million tons, Vietnam, 3.6 million tons, Bangladesh, 2.2 million tons, Egypt, 1.4 million tons, Norway, 1.3 million tons, Chile and Myanmar, 1.0 million tons, and Thailand, 0.96 million tons. The top 10 producers collectively contributed 89.3% to the world production by quantity in 2016. Fish farms, if are well designed, constructed and operated based on the specified standards and assigned safeguards, are safe and have no environmental risks. However, Egyptian Dutch Advisory Panel on Water Management, AP, proved that the random privately designed and poorly operated local fish farms embed several environmental risks and hazards too. Fish farming in Egypt and worldwide. Fish farming, if well designed, operated and managed, is beneficial. Constructing local illegal fish farms without proper planning nor operating contributes to environmental degradation. 3. In Egypt, there is high competition on water resource among the various sectors: municipalities, irrigation, electricity, industry, navigation, and tourism. Furthermore, the freshwater resources of Egypt are limited and consequently comes to be a key national challenge. The escalating population and water pollution increase in Egypt are the main threatening factors. Fulfilling the current and future water demand of the Egyptians are on the top of the agenda of the Egyptian leaders and policy makers. Thus, they strive for identifying the viable and suitable national/regional water strategies and implementation actions that should be applied for future water sustainability and food security for its future generations. Several technical studies and official reports assured that fish farming, if integrated with agricultural cropping cycles, well designed, operated and managed, is beneficial, from the economic and social perspectives and has no negative environmental impacts. On the contrary, converting agricultural plots into fish farms without good design, operation, nor permits is prohibited according to the Egyptian Farmland, Fishery, Marine Wildlife and Aquaculture Conservation Law, Law No. 124 for the year 1983, due to its higher water consumption and negative environmental impacts. One of those key actions according to the Egyptian Water Resources Strategy is limiting water pollution resulting from the expansion of the privately operated fish farms. Especially in the northern parts of the Nile Delta, which is the focus of this research paper. The traditional fish farm systems consist of constructed earthen ponds with size of about 1 feddan, acre, each, with higher dikes allowing water depths to reach 0.75–1.6 meters with average of 1.0 m. It is noted that fish feeding allows for growth of biological oxygen demand, BOD, in ponds water. Sanyu, 2016, mentioned that ponds have a rate of water renewal to compensate for oxygen shortage, evaporation, and seepage. That rate is about 0.4 to 0.8% of pond volume equivalent per day, occurs periodically through the year using fresh water, agricultural reused drainage water with reasonable quality or nearby shallow brackish groundwater with reasonable salinity less than 5,000 ppm, part per million. 4. The total water requirements for fish farms operation is the sum of water required to initially fill the ponds, the daily renewal water, the evaporation water from the free surface of the ponds and the quantity of seepage water from the bottom of the pond to the soil. Usually the disposed water from fish farms is within half the remaining water in the pond as the rest is fish biomass consumption. 5. According to Salam, 2017, in El Tina Plain in North Sinai of Egypt, land reclamation and soil salts leaching was done concurrently with operation of fish farms. Each fish farming cycle was 9 months, 270 days. Renewal water was about 6% of pond capacity per day. Evaporation rate in El Tina Plain, semi-arid region ranges between 0.4 to 0.8 cm/day, was considered 0.6 cm/day. Seepage water depended on soil type and compaction ratio of the pond's side banks. Therefore, seepage rate of heavy clay soil was assumed as 0.5 cm/day. 6. Estimation of total water consumption for reclamation/leaching and operation of 1 feddan of fish farms in El Tina Plain using low saline water was large, about 128,058 m3/feddan/cycle, equivalent to about 474 m3/day/feddan. That leaching process did not last for long period. The required water for soil leaching and fish farms operation in El Tina Plain consumed about 12 times of the annual agriculture crops water requirements, 2 successive crops per year, each consumes about 4,500 to 5,000 m3/feddan. 7. David Molden et al., 2009, proved that the annual average water requirement for governmental fish farm operation in Egypt was in the range of 10,806 to 9,284 m3/feddan/cycle 8. It was proven also by Salam, 2017, that soil leaching process in El Tina Plain in North Sinai reduced soil salinity at the beginning. However, due to the random operation of fish farms by local inhabitants and small business groups, it was found that soil salinity of the surface layer within the fish ponds increased again by about 20% in relation to its value before fish farms operation. However, for the lower soil layers, soil salinity increases by about 95%. That phenomenon of increased soil salinity after operation of fish farms used to happen in all heavy soils, as well as because of the fish food remainders, residuals and fish feces decomposition in the pond water. Ali et al., 2006, proved that the resultant effluents from fish farms used to include nutrients, phosphorus and biological loads that might be used as agricultural fertilizers, yet if mixed with high concentrations to the recipient surface drainage water and/or shallow groundwater might cause significant pollution. 9. B. Fish farm design. A study prepared by AP, 2010, inferred that the total area classified as fish farms in the northern Nile Delta of Egypt amounts to approximately 248,000 feddan. Cultivation season is from April 1–November 1, meaning 214 days. Flushing/renewal water could amount to some 20% of the pond storage per month, which would lead to a maximum additional water requirement of around 6,000 m3/feddan over the fish cultivation season. Evaporation from open water is in the amount of 0.6 cm/day. No rainfall contribution during the fish cultivation season. Arid and semi-arid zone. Pond bottom at 0.5 m below soil surface and a water depth is about 1.0 m. Resistance of puddled bottom layer and clay cap resistance in association with the fish food residuals and fish feces make seepage from the bottom soil of the fish pond almost nil, few months after operation. As a reflection, the estimation of AP with such assumptions seemed to be conservative to some extent regarding the overall water consumption volume in fish farms per feddan per cycle 2. Abdel Fattah et al., 2015, informed that about 2.38 million feddans, 26% of total irrigated agriculture lands in Egypt, which is about 9.1 million feddans during the study period, is infested with salinity problems among other water pollutants due to practices depending on reuse of agricultural drainage water and saline shallow groundwater. Also, it was mentioned that the phenomenon of increasing the privately operated inland fish farms, illegal and poorly managed, constituted a threat to the Egyptian drainage network and northern lakes' water quality, as those fish farms' effluents disposal included high biological and nutrients loads. It is also known that there are unfortunately additional microbial and heavy metal spills from villages and small industrial facilities to some drainage water network in Egypt. 10. Fish farms' activities are permitted by the Egyptian government policy as far the appropriate safeguards are fulfilled. Most of the governmental, official, and local fish farming are located in the northern parts of the Nile Delta regions and in Sinai. The illegal expansion of privately operated fish farms increased in Egypt 2 decades ago. Construction of fish farms is permitted by the Egyptian environmental laws in lands that are unsuitable for any other beneficial agricultural activities. The Egyptian General Authorities for Fisheries Resources Development, GAFROD, is responsible for giving licenses to construct safe fish farms. Increased attention of the relevant governmental authorities in Egypt has been given to impose rigorous regulatory safeguards for fish farms operation, improve drainage water efficiently and expand the construction of drainage water treatment plans, so as to sustain human health, healthy crops production and environmental quality. 11. Although converting agricultural plots into fish farms is prohibited according to the Egyptian law, number 124 for the year 1983. It was noticed that the privately operated fish farms had increased in the northern parts of the Nile Delta during the last 2 decades, due to its much higher profitability if compared to the traditional agricultural crops. The total area of official fish farms in Egypt is estimated at 283,000 feddans, which represent about 3.1% of the total area of agricultural land, during 2014 to 2015. Almost an equal area is used as private non-official fish farms activities for each. Official fish farm consists of large number of fish ponds, underground impoundments. Fish ponds vary in size from 1 to 25 feddans. The proper spatial planning of the official fish farms zoning, site selection and design of ponds considers the social, economic, environmental, and governance objectives of sustainable development make it of great benefits and environmentally safe. 12. However, the production of official fish farms is low due to the conservative quality measures, if compared to the privately operated fish farms. The main reasons of the privately operated fish farms expansion are the easy, cheap, random, and quick construction, possible usage of saline soil and poor quality water in the proximity of the fish farms, drainage water and/or brackish groundwater, and thus speedy growth of fish due to nutrients exist in the polluted used water leading to high and quick profitability. 4. Regarding fish water consumption, Boyd and Tucker, 1998, informed that most fish farm species biomass is about 75% water. Thus, 1 ton of biomass contains about 0.70 to 0.75 cubic meters of water. According to Boyd, 1982, and U. and Boyd, 1992, seepage to the shallow groundwater aquifer and evaporation from the free fish pond's surface are other elements needed to estimate amount of effluent disposal in the water balance equation of the fish farms. 1415. App. 2010, mentioned that fish biomass growth includes 75% of the fish's weight as water, meaning that fish growth biomass should be among water consumption components in fish farms' water balance equation. See information technology tools used. Remote sensing is proven to be a powerful tool for monitoring changes occur in the physical Earth features, either natural or human-induced activities. To detect and monitor such spatial and temporal changes in considerably large areas, multi-temporal satellite imageries can be used. Huang and Phipps, 2006, described the Landsat satellite multispectral imageries as a promising technique, for example, used for urbanization analysis and for identifying area of irrigated crops. Plot 16. In addition, the Geographic Information Systems, GIS, has shown great potential in supporting the production of detailed spatial and temporal mapping analysis. Landsat satellite imageries used in this research paper have medium spatial resolution, 30 m, compared to other higher spatial resolution satellite images. It is suitable for detecting changes in relatively large areas, especially agricultural lands. To perform change detection using remote sensing, the region has to be defined geographically accurately to avoid misleading results. Collecting ground truth is required for results verification. Additionally, the daytime/month was determined based on the phenomenon that required to be sensed. To detect the changes in any region using satellite imageries, either the original imageries should be compared based on the brightness values of its pixels in each band, or the classified imageries are compared 17. Detecting the changes through comparing the classified imageries is more appropriate to avoid the radiometric differences in the multi-temporal imageries. The research question which was answered in this paper is how to conduct a comparative analysis of the environmental impacts due to the expansion of the privately operated fish farms in 2 pilot study areas in Egypt during the period 2014 to 2018, since increasing rate of such local illegal fish farms was noticed in that period. That period was also selected according to the availability of latest imageries and the drainage water quantities and qualities data. The analysis tackled several environmental aspects: water requirements, water consumption and disposal, catchment drainage rates, drainage water quality, groundwater heads and salinity, and associated socio-economic aspects in the selected study areas. The novelty and originality of this research paper are using a new combination, using GIs and RS techniques, processing actual measurements and conducting scientific comparisons and analysis, in investigating, quantifying and understanding the evolution of the phenomenon of speedy expansion of local and illegal fish farms in the selected study areas, which was not done before in this field through this methodological approach. 2 Materials and methods. Most of the irrigation water for the Middle Nile Delta is provided by monophyria at El-Khanater and Abasria at Zefta, then Bartira, where the Nile water is checked up with barrages. Few supplemental intakes are used for the Middle Nile Delta. The Middle Nile Delta is divided into a number of main drainage catchments, as shown in Fig. 1. El-Gharbia Main Drain, EGD, is located in the central part of the Middle Nile Delta. EGD system discharges annually about 707 million m3 to the sea with an average salinity of 3029 ppm. The average annual total quantity of official reuse of drainage water for agricultural crops from EGD system is about 1.516 billion m3. That is in addition to other quantities being extracted from EGD feeders by farmers as unofficial reuse to compensate the deficit in irrigating their agricultural crops 18-19. Starting 2012 onward, increasing pace of constructing the privately operated fish farms has been detected in the northern Nile Delta. The expansion in the privately operated fish farms in that area might be attributed to the shortage of fresh water needed for irrigating crops, low crop productivity due to soil salinity, fish profitability, and possible poor control of local authority led to illegal expansion of private fish farms. The 2 study areas. This research focuses on 2 pilot study areas in the northern part of Nile Delta in Egypt as illustrated in Fig. 1. The first one is the northern part of El-Gharbia Drain Catchment, NEGD, between latitudes 30 degrees 44 minutes north, 31 degrees 30 minutes north and longitudes 30 degrees 53 minutes east 31 degrees 20 minutes east with area about 485,000 feddans. The second is in the southern part of the Lake Burullus, SLB, between latitudes 31 degrees 17 minutes north, 31 degrees 32 minutes north and longitudes 30 degrees 35 minutes east 31 degrees 09 E with area about 152,755 feddans. Total study area is 637,755 feddans. B. Methodology and assumptions. 5 relevant research aspects were included in this research paper to fulfill the target of analyzing the evolution of environmental impacts due to fish farms expansion in the study areas. Those aspects include changes in 1. Surface area, 2. Catchment drainage rates, 3. Surface water quality, 4. Groundwater heads and salinity, and 5. Economic and social conditions. Determining the fish farms area is essential to estimate the water requirements of fish farms. Knowing the drainage rate is necessary to estimate the disposed effluent from fish farms in the study areas. As fish farm activities affect both surface and groundwater quantities and qualities, therefore this research paper focused on both drainage water and shallow groundwater. The socio-economic aspects are important as fish farm business is of high profitability, so that banning or controlling it would have negative impacts on families using it for their livelihood and life sustenance. Multispectral Landsat-8 imageries were processed, where the principal component analysis, PCA, was conducted to the 2 dates images. Then the Landsat imageries were classified and compared. The research period, 2014 to 2018, was selected according to the availability and quality of Landsat-8 imageries as well as drainage water quantity and quality availability. Estimating the expansion of fish farms during the period, 2014 to 2018, in the study areas was accomplished through Landsat-8 satellite imageries analysis and classification, followed by identification of the fish farms in the images of the two dates. Then the change in land cover, especially the fish farms, were detected and areas were calculated. Verification was made through field checks. The actual measured catchment drainage rates, surface water quality parameters and groundwater heads and salinity status were obtained from authenticated official sources, databases of the specialized research institutions under the National Water Research Center of Egypt, where the three authors belong to. The following are a set of assumptions used in this research paper. The aim is conducting a comparative analysis of the environmental impacts between years 2014 and 2018, rather than environmental impacts assessment. Therefore, the changes and/or differences in estimation of fish farms area, catchment drainage rates, water quality, and groundwater status were the focus of this research during the period 2014 to 2018, not the absolute values nor numbers. Expansion of fish farms in the study areas, NEGD and SLB, was attributed to the increasing rate of constructing the privately operated fish farms by local communities, small business groups and inhabitants. The reason is because the government authorities emphasized that there were no official fish farms constructed in the study areas during the period 2014 to 2018. Based on the literature review, relevant technical studies, experiences, and the various stated characteristics of fish farms design in the Nile Delta of Egypt, the authors determined the characteristics of a typical unit fish pond, 1 feddan, as shown in Table I. It was considered that fish biomass amounts to about 50% of the remaining pond water as per the used water balance equation. The normal practice followed in villages and local communities in the North Nile Delta of Egypt is that water requirements for their fish farms are pumped from the nearby drainage network and/or abstracted from the shallow groundwater aquifers in the fish farms areas. Then, the effluent discharge is disposed to the closest drain, pond, wetland, or lake. Water balance equation used for each fish pond, unit pond area is 1.0 feddan, is as follows, units used are m3/feddan/cycle. Volume of the pond plus volume of renewal water equals water equivalent to fish biomass plus evaporation plus seepage plus effluent discharge. The calculations and analysis in this research paper were conducted based on assumptions, scientific concepts, critical review of literature, land truthing, previous relevant technical studies and similar conditions in Egypt and in other countries as presented in this research paper, as shown above. Table I presents accordingly the calculations of fish pond components according to the water balance equation. 3GIs/Rs data description and processing. Fig 2 illustrates the entire Nile Delta region where 4 Landsat-8 satellite imageries were assembled. Fortunately, most of the study areas considered in this research paper appears in one Landsat satellite imagery, path 177, row 38, covering around 80% of EGD catchment area and the entire area of SLB. One of the techniques used to analyze the multispectral remote sensing data that has proven to be of value, was the Principal Components Analysis, PCA, in which, the original remotely sensed datasets, bands of satellite imageries, are transferred to a smaller set that is easier in interpretation. Those imageries were uncorrelated and represent most of the information shown in the original datasets 20. The workflow of processing change detection used in this research is illustrated in Fig 3. The details of this procedure is as following. 2 Landsat-8 imageries, path 177, row 38, representing the 2 years of comparison, 2014 and 2018, were downloaded, from the U.S. Geological Survey, USGS, website, to determine the changes in fish farms areas expansion within the 2 study areas NEGD and SLB. Since Landsat imageries contain relatively large number of bands, only bands that gave large reparability between classes were considered. However, such agricultural lands needed due attention to distinguish fish farms from the other unclear water bodies, such as rice fields or uncultivated ponds and wetlands. The downloaded Landsat-8 imageries were selected to be acquired within the month of March, 2014 and 2018, when the rice crop is not in the field. Rice usually is cultivated in early May and harvested in August every year. That is to avoid confusion in misclassification between rice fields and fish farms, since both rice fields and fish farms are covered by water. The swamp/ponds areas were also excluded based on its identified footprint. Fig 4 shows the 2 Landsat-8 imageries for years 2014 and 2018, in false color, R, B4, G, B5, and B, B2. The second step was rectifying the satellite imageries, where both imageries had to be geometrically corrected to ensure that the study areas are correctly spatially defined on both imageries. In this research paper, no ground control points were available, therefore registering one image to the other was the choice to geometrically correct the imageries. The downloaded imageries were georeferenced, hence, the spatial location of both imageries was compared. It was found that both imageries were coinciding, and no further registration was required. Nevertheless, 20 well-distributed points were selected inland on both imageries to act as check ones. By comparing the positions of the 20 points, it was found that the total root mean square error, RMSE, is about 4.6 m. The third step was applying the principal components analysis, where the important information of the Landsat-8 bands concentrated on the first three uncorrelated bands. Fig 5 illustrates the PCA images for the 2014 and 2018. For change detection processing, when the imageries are classified first, then the classification results are compared. No radiometric correction is required. 17. Therefore, in the fourth step, the principal components imageries were classified using the maximum likelihood classification algorithm for both image rise of the years 2014 and 2018. The maximum likelihood classifier is a supervised classification technique that intensively used with the multispectral remote sensing data. In this algorithm, the probability of each pixel to be belonging to each of the predefined classes is calculated. Then the pixel is assigned to the class of the Heights probability 17. The classification results within the study areas, NEGD and SLB, are illustrated in Fig 6. A number of locations that were classified as fish farms were selected to be used as ground truthing for verifying the classification results. The coordinates of the selected fish farms were determined from the satellite images. The ground truth was collected by technicians from the DRI. The locations were identified using the Global Positioning System, GPS, in association with those locations' coordinates. The privately operated fish farms were found in the proper locations as in the imageries with 95% accuracy. In addition, the identified fish farms were found inside the drainage catchments of Sigaya Pump Station, PS, called MG02, Mehalat Ruh PS called MG03, Samate PS called MG04, PS. Number 5 called MG05, and PS. Number 6 called MG07, within EGD catchment. In the fifth step, the area of the fish farms in both imageries were calculated. And the difference in areas between years 2014 and 2018 for the two study areas were determined and shown in Table 2. For results and discussions. A. Expansion in fish farms areas. One of the objectives of this research paper is to determine the change in area of fish farms during the period, 2014 to 2018. Since the GAF reported that there were no additional official fish farms constructed in the two study areas, NEGD and SLB, during that period, the expansion in fish farms was certainly due to the construction of the privately operated fish farms, without knowledge of local authorities. Based on the analysis, change detection process, of the Landsat-8 satellite imageries, it was found that fish farms area had increased from about 248,194 feddans to about 266,613 feddans during the period, 2014 to 2018, as illustrated in Table 2. Expansion in the privately operated fish farms area during the period, 2014 to 2018, was recorded along those 4 years in NEGD about plus 7,508 feddans, 27.11%, and in SLB about plus 10,911 feddans, 4.95%, of the study areas. The overall increase in fish farms area was estimated about 7.42% of the study areas during the period, 2014 to 2018, which is equivalent to about plus 18,419 feddans. B. Estimation of water requirements of the privately operated fish farms. Total annual water requirements for one feddan of the privately operated fish farms in the study areas was estimated about 17,803 m3/feddan/cycle, year, based on calculations in Table I. That amount is equivalent to about 82 million m3/year, 328 million m3 in 4 years 2014 till 2018, based on Table 2. That amount was pumped by the private fish farms operators from the nearby sub-drains of EGD as well as abstracted from the shallow groundwater aquifer in the study areas. Table 3 shows the details of increase in water requirements for the privately operated fish farms expansion in the study areas during the period, 2014 to 2018. The average crop water requirement per season in Egypt is about 5,000 cubic meters, while there is a rotation of two sets of main crops in Egypt, summer crops and winter crops. Therefore, total crop water requirements in Egypt per year is about 10,000 m3/feddan. Accordingly, ratio of crop water requirements to fish water requirements in the study areas during the study period was about 1:1.8, almost double. The fish biomass was assumed about 50% of the remaining pond volume of water, which was about 5,700 to 5,800 m3/feddan/year. According to the water balance equation used, total effluent discharge from the privately operated fish farms was estimated about 5,756 m3/feddan/year during the period, 2014 to 2018, equivalent to about 26.5 million m3/year, 106 million m3 in 4 years. That significant amount of effluent with high pollution loads, biological, nutrients and microbial, used to be disposed into the nearby water bodies, causing pollution problems possibly affecting all surrounding activities, human, agricultural crops, cattle and sheep production and fish production in the neighborhoods of the recipient drains and lakes. El-Gharbia, 2016, affirmed that the most likely reasons of water quality deterioration in the last reaches of El-Gharbia Drain were excessive usage of drainage water to supplement the shortage in fresh irrigation water, and in addition, the improper privately operated fish farming practices. 21. See changes in catchment drainage rates within the study areas during 2014 to 2018. The drainage rates, DR, is defined as sum of agricultural drainage water, from crops and fish farms, sewage effluents and industrial effluents of a catchment to a certain point on a drain. The DRS of the drainage network in Egypt used to be measured and calculated by DRI of the National Water Research Center of Egypt. The drainage rates estimation is based on the multiplication of catchment area served by each drainage pump station, PS, within the study areas by its measured discharge, in mm/day. Based on the actual geographic layout of the study areas, the authors realized that the NEGD catchment could be represented by 3 pump stations, Sigaya PS, MG02, Mehalat Ruh PS, MG03, and Samate PS, MG04, whereas SLB catchment could be represented by 2 pump stations, PS. Number 5, MG05, and PS. Number 6, MG07. All 5 pump stations are located inside the study areas, NEGD and SLB. Table 4 presents the details of estimating the annual change in drainage rates resulting from all human activities in the study areas during the period, 2014 to 2018. Accordingly, it was estimated that drainage rate decreased in NEGD by -0.03 mm/day, while decreased by -0.11 mm/day in SLB during the period, 2014 to 2018. The reuse of drainage water in agriculture, due to shortage in fresh irrigation water, as well as the operation of the private fish farms in the study areas, consumed large amount of El-Gharbia drain water, causing that decrease in drainage rates and consequently drainage quantities in the study areas. This reduction was estimated in average as 41.2 million m3/year, during the period, 2014 to 2018. The available measured historical average annual catchment drainage rates during the period, 1984 to 1990, were collected from the DRI database to illustrate evolution of annual drainage rates within the study areas. Fig 7 presents the analysis done in this research on the drainage rates data sets, showing an overview of the changes in drainage rates within the study areas during the period, 1984 to 1990, compared to the study period, 2014 to 2018. That analysis showed annual decreasing trend of drainage rates. It was found that continuous reduction in drainage rates by more than 30% if the two periods are compared. This could be attributed to the expansion in agriculture activities and unofficial reuse of drainage water in the study areas, which agreed with the author's findings in this research paper. Same findings were also emphasized by DRI, 2016. It added that portion of the drainage water flowing to Lake Burullus from the study areas, through El-Gharbia Drain, decreased during the years, 1984 till 2018. That could be attributed to the expansion in unofficial reuse of drainage water for irrigating agricultural crops as well as to fish farms operation. However, DRI also proved that the annual average drainage water flowing into Lake Burullus from all its feeders increased from 0.53 to 0.71 billion m3/year during the same period. D. Changes in water quality of agricultural drainage water within the study areas during the period, 2014 to 2018. Observing the drainage water quality status in the study areas based on the DRI databases during the years 1984 till 2018, it was noticed that salinity of the drainage water flowing to Lake Burullus from El-Gharbia Drain increased during 1984 till 2012, yet continued to increase with higher pace after that till 2014 and afterwards. Salt load of the drainage water flowing into Lake Burullus from El-Gharbia Drain increased from 1.5 to 2.1 million tons/year during the period 2014 to 2018. That finding was evident of multiple reuses of drainage water practiced by farmers for securing irrigation water for their crops in the study areas. In general, majority of the recorded water pollutants in El-Gharbia Drain were high nutrients, biological, microbial and heavy metals constituents, beyond the environmental law protection of River Nile and its tributaries from pollution number 48 for the year 1982, modified in September 2018, illegal fish farms activities and disposal into the small drains flowing into El-Gharbia Drain and Lake Burullus could be direct reason for those high recorded water pollutants. A more in-depth overview of the average annual water quality parameters values in the drainage water within the study areas due to expansion in reuse of drainage water as well as in privately operated fish farms in NEGD and SLB during years 2014, 2016 and 2018, are shown in Table V. It is obvious from Table V that high pollution concentrations were detected in El-Gharbia Drain during the period 2014 to 2018. The privately operated farms' expansion in the study areas contributed significantly to deteriorating water quality of the surface drainage water during the study period as a result of 1. Reusing drainage water multiple times and 2. Disposing fish farms' effluents with high pollution of biological and nutrients loads. Previous studies concurred with those findings, as they agreed that intensive fish farming can lead to higher proportion of organic matters and fertilizers residuals such as ammonia, nitrite, and phosphate compounds as well as high proportion of heavy elements in the water and sediments 22, 23, 24, 25, 26, 27, 28. Abdelmegid, 1998 and 1999, mentioned that as a consequence of having fish farms activities, its nutrients effluent caused increase in phosphates and nitrates concentrations in the drainage water, probably causing spread of algae of various kinds, as well as formation of a suitable environment for the growth and spread of many diseases that can lead to health problems for the consumers, either in direct and/or indirect contacts. 29, 30. Also, in this context, the previous researches informed that consumption of food and deposition of fish fecal matters in the surface drainage water network may further stimulate the growth of phytoplankton and filamentous algal because of the presence of nutrients 22, 23, 26, 31, 32, 33, 34, 35. Such nutrients may constrain water use in ponds by enhancing the process of eutrophication, increasing the inorganic and organic sedimentation and causing ecological environmental pollution, water, sediment, flora, and fauna. It was also mentioned that anoxia may be established in the water column a few centimeters from the zooplanktons, benthos, and fish particularly diminish causing sensible pollution 9, 27. Therefore, expansion of illegal fish farms in the northern parts of the Nile Delta affects all surrounding activities, human, agricultural crops and cattle and sheep production in the catchments of the recipient drains and lakes. Thus, impacts of the privately operated fish farms should be strictly overcome by all means to sustain water, food, and environment in healthy state. This may require relevant awareness programs to the local communities, inhabitants, cooperatives, and small business groups in the study areas, its surroundings and the whole Nile Delta aiming at explaining the danger of spread of illegal fish farms. Changes in groundwater status within the study areas during 2014 to 2018. The ministries responsible for water resources and agriculture in Egypt declared the official fish farms that depend on brackish groundwater in Egypt. The privately operated fish farms were not included in that declaration, Fig. 8. The concerned study areas were located within that zone above the northern Middle Nile Delta aquifer. The Nile Delta aquifer is one of the largest aquifers in Egypt. It starts at the south of the delta at El-Qanater city with an average thickness of 200 m and gets deeper when heading towards the north, reaching a saturated depth of 1000 m at the sea coast. The Nile Delta aquifer has a complex geological formation. The northern part of the aquifer comprises of a multi-layered aquifer system, while in the southern part the aquifer consists of sand and gravel facies 36. The salinity of its groundwater changes according to the depth of the water beneath the soil surface and its closeness from the sea. Groundwater categories ranging from fresh to brackish to saline to brine groundwater 39. Brackish and saline groundwater can be used for all fish farming activities. During the concerned study period, 2014 to 2018, groundwater heads and salinity data were utilized from National Groundwater Quality Monitoring Network, NGWQMN. NGWQMN is established in the 90s to provide information needed for planning, management, and development of groundwater supplies to meet current and future water needs and ecosystem requirements. The network consists of groundwater observation wells distributed all over the country, with focus on areas with high agricultural and industrial activities. The observation wells were implemented to monitor different depths in the aquifers, from 40 to 1,100 m, in terms of groundwater heads and salinity. Fig 9 shows the depth to groundwater in the study areas during 2014 and 2018, investigated and interpolated from NGWQMN database. It was found, based on the few available groundwater data, groundwater depths and heads, within the study areas, that there was a general increasing trend in groundwater depths, which means decrease in groundwater heads. The change could be interpreted by the unplanned increase in groundwater extraction by farmers and could also be explained by the expansion of privately operated fish farms and supplementary crop irrigation in the study areas. This situation also affected the salinity of the groundwater but in a lesser impact. The salinity of the shallow groundwater has decreased slightly in the study areas in a range from 50 to 1,100 ppm during 2014 to 2018, 36, 37. This could be attributed to the seepage of excess irrigation water downward into the shallow groundwater, mainly drainage water with less salinity than the groundwater in that area. However, to study the particular impact of the privately operated fish farms expansion, it is recommended that shallow groundwater observations wells, 10-20 meters depths, to be drilled around those fish farms locations in the study areas. The wells have to be implemented with different distances from the fish farms. Hence, these wells can monitor, locally, the change in groundwater heads and salinity when regularly observed. The impact of those fish farms on groundwater could then be determined accurately, in terms of quantity and salinity. Economic and social prospects of fish farms expansion shading light. Expansion of the privately operated fish farms in the Nile Delta in the last decade has been due to its easy, cheap, quick construction and speedy growth of fish due to nutrients exist in the polluted water used, leading to high and quick profitability. Accordingly, thousands of families live in the northern parts of the Nile Delta became fully dependent on those fish farms' jobs, direct and indirect, to cover for their living expenses. On the other hand, converting the agricultural crops plots into fish farms in such large pace affected the national production of agricultural crops. Even the neighboring farmers who stick to cultivating agricultural crops suffered significantly from fresh irrigation water shortage being at the end of the irrigation system as well as shortage in drainage water due to the high water consumption used in the nearby fish farms. The new Egyptian Water Resources Law issued and endorsed in 2019 by the Egyptian People Assembly as well as its implementation bylaw tackle properly the violation of those privately operated fish farms. However, it is recommended that a detailed cost-benefit analysis as well as socio-economic study to be conducted on the impacted communities in the study areas and elsewhere. Based on the results of those studies, the Egyptian government and its local authorities are encouraged to avail alternative suitable jobs opportunities with relatively equivalent earnings to the owners, operators, and workers of the privately operated fish farms in Egypt, so that those inhabitants can continue having good livelihood without hampering the efforts of the Egyptian government in combating pollution. Conclusion and recommendations. This research paper proved an increase of 7.42% equivalent to an area of 18,419 feddans of privately operated fish farms on the expense of the agricultural crops in the study areas in 4 years during 2014 to 2018. Also, it was estimated that annual increase in water requirements due to those privately operated fish farms expansion during 2014 to 2018 was about 82.0 million m3/year. The ratio of water requirements, fish versus crops, in the study areas was estimated almost double. The estimated increase in disposed effluent from the privately operated fish farms in the study areas to either nearby small drains or lakes was about 5,756 m3/feddans/year, 27 million m3/year from the study areas, equivalent to an increase in drainage water about 106 million m3 from the study areas in 4 years, 2014 to 2018. Although expansion in the privately operated fish farms in the study areas during 2014 to 2018 added large disposed effluent to the drainage system, the resultant was a decrease in drainage rates by more than 30% from the whole study areas. This could be attributed to the growing unofficial drainage water reuse from El-Gharbia Drain System, causing a decrease in drainage rates from the study areas estimated about 41.2 million m3/year during 2014-2018. High pollution concentrations were monitored in El-Gharbia drain system during the period 2014 to 2018. A number of water quality parameters sometimes exceeded the environmental law limits by many folds. The privately operated fish farms expansion in the study areas contributed significantly to the deterioration of water quality of the final reaches of El-Gharbia drain during the study period due to its effluent discharges with high biological and nutrients loads. It was noticed that a general increasing trend prevailed in groundwater depths in the study areas during 2014 to 2018. That could be interpreted by the increase in unplanned groundwater extraction by farmers for supplementary irrigating their crops as well as operating the expanded privately operated fish farms in the last years. However, salinity of the shallow groundwater has slightly decreased in the study areas, ranges between 50 and 1100 ppm, during 2014 to 2018. It is recommended that expansion of privately fish farms in the northern parts of the Nile Delta should be strictly controlled by law to sustain water, food, and environment in healthy state. The National Water Quality Monitoring Network needs to be strengthened and modernized. Its measured data should be processed then integrated in the decision-making systems, research and government institutions. Shallow groundwater observation wells need to be drilled in the study areas for detailed analysis of the impacts of the privately operated fish farms expansion on the groundwater. It is worth to establish relevant awareness programs and avail alternative suitable jobs opportunities to the local communities, inhabitants, and small business groups in northern Nile Delta to explain the risks and danger of spread of random fish farms. Acknowledgements. The authors acknowledge the sincere effort done by the researchers and scientists of the National Water Research Center of the Ministry of Water Resources and Irrigation of Egypt in identifying, collecting, and availing the required data for this research paper, in particular the Drainage Research Institute, the Survey Research Institute and the Research Institute for Groundwater. Deep appreciations are due to the chairpersons, directors, managers, and experts of the Ministry of Water Resources and Irrigation of Egypt, who gave sincere advices, enlightening remarks, and critically reviewed this research paper. Additionally, the authors would like to thank the USGS to make Landsat images available for research.